To recall from our last video, instructions are a segment of code containing steps that need to be executed by the processor. It can be divided into three parts: addressing mode, the opcode, and the operand. The opcode is the portion of the instruction that specifies the operation to be performed. The operand is the object on which operations are performed. Say you give your system an instruction, add 2 and 5. The values 2 and 5 are called operands. By definition, the object and quantity that is operated on is called an operand. Here, add is the opcode. The opcode says what to do with the operands. In this video, we will look into some of the types of instructions. Instructions can be broadly divided into three categories. Firstly, there are data transfer instructions. Instructions that move data from and into registers, main memory, stack, or I/O. Then there are data processing instructions that perform arithmetic and logical operations. Lastly, there are control instructions that help in systems control and transfer of control and help keep the functioning of CPU smooth. Data transfer instructions. As from the name, these instructions are used to transfer data from a source operand to a destination operand. The operands can be anything from a register to a memory location. As said before, these instructions move, store, load data from and into registers, main memory, stack, or I/O. These instructions can be used to copy data from a memory location to a register or vice versa. The instruction move is used for this. The instruction store is used to store the contents of a register or the result of a computation, and the instruction load is used to retrieve stored data to perform a computation on it later. An example of data transfer instruction would be MOV AX. This instruction copies value in AX register to BX register. Another example, LDS BX 4326. This loads content at memory address 4326 to the register BX. Data processing or data manipulation instructions. There are three further types of data manipulation instructions. The first one is arithmetic instructions. These instructions are used to perform arithmetic operations like addition, subtraction, multiplication, division, etc. It may also include increment, that is A++, or decrement, that is A minus minus, negate, that is minus A, addition with carry, and subtraction with borrow. An example of arithmetic instruction would be add AL 74H. This instruction adds number in the address 74H to the content of AL. Another example of arithmetic instruction would be DIV-BL. This instruction divides the word in the register AL by the byte in BL. Secondly, we have logic and bit manipulation instructions such as AND, OR, XOR, NOT. An example of logical instruction would be AND BHCL. This instruction would compute logical AND on the registers BH and CL and store the result in BH register. NOT BX. This instruction inverts content of BX register. Lastly, there are shift and rotation instructions. These include commands such as SHR, logical shift right, and SHL, logical shift left. The purpose of each shift instruction is to shift an operand bit by bit to the right or left. In SHL, logical shift left, the highest order bit is shifted out. Then each bit is shifted one bit to the left. Then 0 is shifted in. In SHR, the logical shift right, the lowest order bit is shifted out. Then the remaining bits are shifted to the right one by one. Then 0 is shifted in. In the next category, we have control instructions. Generally, CPU executes instructions in sequence. Program control instructions dictate the sequence in which the program is executed. It provides control over the flow of the program and provides the capability to branch to different program segments. Some of the common instructions under control flow instructions are Unconditional Branch Instruction. This instruction instructs the control flow to branch to another location in the program and execute instructions there. Conditional Branch Instruction. This instruction instructs the control flow to conditionally branch to another location if a certain condition holds. Call. This instruction calls another block of code while saving the location of the next instruction as a point to return to. In call, program control is transferred to a memory location which is not a part of the main program. Jump. This instruction lets the program to jump to different segments of the program like functions, subroutines, etc. Unlike call, in jump, program control is transferred to a memory location which is in the main program. An example for control instruction would be compare AX 4371H. Jump if above to next. This instruction subtracts 4371H from AX and jumps to the label next if AX is above 4371H. The next example, call BX. This transfers the program control to the register BX, which is not a part of the main program that is currently being executed. Finally, let's see how various types of instructions are used together. To demonstrate interrelated instructions, we will see an example where a combination of instructions are used to find a factorial of a number. First, the program initializes the AL register with 1. Then, the program stores the BL register with a number we want to find the factorial of. In this case, the program is to find the factorial of 3. Now, under the label look, the program multiplies AL register with a number in BL and stores the result in AL. AL now is equal to AL into BL. Then decrements BL by 1. So BL now becomes 2. Now the jump if not 0 instruction checks if BL is 0. If not, it jumps to the look label and multiplies AL with BL and stores the result in AL. Then decrements BL. So now AL is equal to AL into BL is equal to 3 into 2 and decrements BL from 2 to 1. Since BL is not 0, it repeats the instruction under look. The program multiplies AL register with the number in BL and stores the result in AL. So now AL is equal to AL into BL, 3 into 2 into 1. Then decrements BL by 1. So BL now becomes 0. The system now checks if BL equals 0. Since BL is 0, the system doesn't jump to the look label but instead proceeds with the natural sequence, thus reaching end. If supposing BL was non-zero, the loop runs again by jumping to the look label and repeating the instructions under look until BL is 0.